Hello and welcome. In this video, we are going to work some more on calculating Riemann sums by hand, focusing on different types of Riemann sums, such as midpoint, right-handed, and left-handed. And then we're going to talk about how to make our approximation better and how maybe we could go about this whole process without actually having to draw rectangles each time to approximate the area under the curve. So that idea is going to extend into a definite integral that we can actually calculate without Riemann sums. So I look forward to jumping into this with you. So jumping back into where we left off in the last video, we are going to be approximating the area under the curve from 0 to 6 of this function graphed here. And the function that's graphed here is this function, the square root of x squared plus 10. And again, we're starting at 0 and we're stopping at 6. So we're looking at this area that's being formed under the curve here. We're going to find the area under the curve. So this would read out loud the integral from 0 to 6 of the square root of x squared plus 10 dx, meaning we're finding the area under the curve between 0 and 6 of this function. So we are specifically being told to use a midpoint Riemann sum with 3 equal subintervals. So looking at this, if I needed to cut this length 6 into 3 equal pieces, 1, 2, 3, they're each going to have a width of 2. And then the height is going to be determined in the way that they're asking us to do this. So I'm going to erase what's here so we can draw those rectangles a little bit more clearly. So to get an idea of what our height is going to be, we have to look at the midpoint between each of these intervals. So the first one we're looking at is the midpoint between 0 and 2. Well, halfway between 0 and 2 is 1. We can't tell exactly what the height is there, but I'm going to sketch my rectangle here. We can't tell exactly what the height is from the graph. We're going to remind ourselves that we can find the height from the function, but that's going to be our first rectangle. Our second rectangle, we're looking between, so this was, we were looking at 1. We're going to be looking between not 0, but 2 and 4, which means we're going to be looking at 3. So our height is going to be wherever the function is when we're at 3. And I'm going to go ahead and draw my rectangle here. And then we should have one more rectangle. And that rectangle is going to come into place when we're halfway between 3 and 4. Sorry, not 3 and 4. 4 and 6. Which means at the height of 5. Or not the height of 5 when the x value is 5. So there is our third rectangle. So now our goal is to find the area of these 3 rectangles and add them together. So let's look at each one. So the area of the red rectangle is going to be the width, which is 2, times the height, which in this case is what we get when we plug 1 into our function. And actually, since this function isn't defined, I'm going to just go ahead and plug 1 into the function that they gave us, what we get when we plug 1 in here. Well, if we simplify this, this is just going to be 2 times the square root of 11, and we're going to go ahead and just leave it like that, 2 square root 11. Now, if I was to find the area of the blue, again, my width is 2, and my height, we said, is what we get when we plug 3 in, so that's going to be the square root of 3 squared plus 10. This is going to be 2 times the square root of 19. And last but not least, our purple rectangle has a width of 2 and has a height of what we get when we plug in 5. So the square root of 5 squared plus 10, which is going to be 2 times the square root of 35. So what we were being asked at the beginning of this problem was to approximate this integral. So the integral from 0 to 6 of the square root of x squared plus 10 dx, don't forget that dx, is approximately, we're not using an equal sign because we're not finding the exact area, we're approximating the area under the curve using midpoint Riemann sums. And this is what we get if we just add all 3 of those values together. So 2 root 11 plus 2 root 19 plus 2 root 35. That is our approximation, units squared. So let's go ahead and look at a couple more examples together, and then I'm going to have you try a couple on your own. All right, so here we go. Approximate the integral from -2 to +2 of the area under the curve of 2 to the power of x minus 2 dx using 4 equal subdivisions. So go ahead and pause the video and see if you can figure out where those 4 rectangles are going to be using either the graph on A or B. So here you can see I've drawn out where the rectangles are going to come from. It looks like each rectangle is going to have a width of 1 in order for us to have 4 equal subdivisions. For part A, we're going to find right-handed Riemann sums. And for part B, we're going to find left-handed Riemann sums. So that's telling us how we're going to find the height of each individual rectangle. Now remember that if the area is below the x-axis, we count that as negative area. And if it's above the x-axis, we count that as positive area. So if you're feeling confident, go ahead and pause the video and just sketch the rectangles for part A and part B. And then unpause the video and see how you did. Okay, if I'm doing right-handed rectangles, then I'm going to use the right-handed point of each rectangle as the height. So here's this rectangle. Here's this rectangle. I'm going to use the right-handed point as the height here. This rectangle is going to have an area of 0. And then last but not least, this rectangle over here. If I'm using left-handed, then I'm going to make the height go down as far as the left-hand point on each integral. That's not very straight. So here, here, this one is going to come down to here. And then our last rectangle, in this case for left-sided, is going to have an area of 0 or a height of 0. Now, if you're feeling confident, see if you can find each of these areas and add them together. So here, this height is going to be what we get when we plug in -1. So to find the area of the red rectangle, we're saying the width, which is 1, times the height, which is f of -1. If I plug -1 in here, and I'm going to just do this off to the bottom, f of -1, 2 to the power of -1 is -1/2 minus 2. This is going to be -1.5 or -3/2. Similarly, for the blue rectangle, let's actually blue, come down here. The blue rectangle is going to have a width of 1, and it's going to have a height of whatever we have right here. This is f of 0. So if I plug 0 in, I get 2 to the power of 0 minus 2. Anything to the power of 0 is 1, minus 2 is -1. That makes sense that both of those numbers should be negative. We already said that our purple area is 0. And if you want to think about that, it would be the width 1 times the height 0. And then last but not least, the black area here would be our width 1 times this height over here, which appears to be f of 2. F of 2, if I plug 2 in, I'm going to get 2 squared, which is 4, minus 2 is 2. So I'm going to get 2. So if I'm approximating the area under the curve, so the integral from -2 to 2 of 2 to the x minus 2 dx, I'm saying that that area is approximately -3/2 minus 1 plus 0. I don't really want to write that, plus 2. And if I was going to simplify this, so that area is approximately -1/2. So this is our approximation, and I'm going to say units squared. This is our approximation using a right-handed Riemann sum. Go ahead and pause the video and work through the left-handed Riemann sum on your own. So here, our height for the red rectangle is going to be what we get when we plug in -2. 2 to the -2nd power is 1 over 2 squared, or 1/4, minus 2. And this is going to give me -1 3/4, or -7/4. So our area is 1 times -7/4. The blue area, we already found this value, f of 1. We found that over here, which is -3/2, so 1 times -3/2. The purple area now is going to be the area that we get when our height is f of 0, which we said is -1. And then the black area that we get here is going to be 0. We can see that from the picture. So all of this area that we're actually calculating is below the x-axis now. So it's all going to be negative area. So the integral from -2 to 2 of 2 to the x minus 2 dx is approximately negative 7 over 4 minus 3 over 2 minus 1. This is going to be negative 4 1/4, or I hate mixed numbers like this, so negative 17 over 4 units squared. So if I was to ask you which of these is a better approximation of the area under the curve, I'm hoping that you can see that A is definitely better in the sense that we didn't include any positive area at all on part B. Everything was negative, and definitely there's more negative area than positive area, but to ignore the positive area altogether definitely seems like it's going to make an underestimate. So what I'm going to do now is I'm going to put up 2 more examples, and I'm going to have you work through those 2 examples on your own and see how you do. All right, here we go. Write each area as an integral, then determine the area under the curve using right or left endpoint rectangles with equal widths. So depending on the particular problem. So you're going to rewrite each of these as an integral. Why don't you go ahead and do that part first, rewrite it as an integral, and then unpause the video and see how you did. So hopefully you had some time to try that, and now you can see we're just writing the integral from the smaller to the larger part of the interval, 0 to 3 or 0 to 2, of the function that they're giving us, negative 2x plus 6 or x squared plus 4 dx. And you don't have to have the parentheses there. I just think it makes it really clear that we're talking about integrating that particular function. What you need to do next is actually to approximate that area using rectangles with equal widths. So over here we're going from 0 to 3, and you're looking for rectangles that have equal widths. Over here we're going from 0 to 2, and you're looking for rectangles that have equal widths. And then this is asking you for right endpoints, and this is asking you for left endpoints. So go ahead and pause the video and work through those on your own. So there's definitely different ways you could cut this up to be rectangles of equal widths. You could have each of them go by a half or a fourth or however you want in this picture. I chose, so your answer may be different than mine, but I chose to make each right-handed endpoint on number 4 be an integer because I felt like that would make my math a little bit easier here. So I constructed it using 3 rectangles of equal width. You also could have done more rectangles of equal width. You could have divided it up along each actual sort of line that they have in this graph and created more rectangles, and that would probably give you a more accurate estimate here. So using what I came up with, the area of this rectangle is going to be, the width is 1, so 1 times the height is 4. The area of my blue rectangle, the width is 1 again, and the height is 2, so plus 2. And the last one has an area of 0, so we're saying this is approximately 6 units squared. What I want you to see is if I had done rectangles, if I had more rectangles here, that's going to give me a better approximation than what I just did, and I still would have equal width. So if you set up your rectangles like this and you added all those areas together, that's totally fine. You're going to have some more fraction work here, but your estimate is going to be closer to the actual value of the area under the curve. And in fact, since this is a triangle, since we're looking at a line here, we could find the exact area under the curve simply by finding the area of the triangle, which would be 1/2 the base, which is 3 times the height, which is 6. So the actual area would be half of 18, which is 9 units squared. So my approximation of 6 is really not that great of an approximation. If I used each of these red rectangles, I probably would have gotten a lot closer to 9. All right, moving on to number 5. So again, since the directions here, the only requirement is that we were using rectangles with equal width, there are many correct right answers here. So I am choosing to look at 2 rectangles. So each of those rectangles would have a width of 1, and then I'm going to add the area of those 2 rectangles together. But again, if you used more rectangles, you're getting closer to the actual area. And since this problem doesn't give any other specifications, both answers would be accurate. So let's go ahead and look at this. If I find the area of the green rectangle, which has a width of 1. So this integral is approximately width of 1 and height of 4. So that's going to have an area of 4 plus width of 1 and height of 5. So this is going to have an area that is approximately 9 units squared. But if we had constructed left-handed rectangles and had more of them, and this is actually going to lead into our next idea, if I used more rectangles, the better the approximation, because look at all this extra area that I'm including now that I wasn't including before with my approximation. So if we want to improve the approximation, how do we do that? That's what we're going to look at next. So what we just saw in those last two examples is that the more rectangles we have, the better the approximation we're going to have. So if we wanted to find the exact value of the area under the curve, we would need an infinite number of rectangles. So what we're saying is more rectangles gives us a better approximation for the area under the curve. But sometimes we need things to be exact. To find the exact area under the curve, we would need an infinite number of rectangles. And that just seems impossible. How can we possibly calculate the area of an infinite number of rectangles and add them all together? And the way that we can do that is by using something we learned quite a while back. We can think about the limit. So the limit as the number of rectangles goes to infinity of what we're looking for. So this right here is some really fancy notation for really just saying the area of each rectangle. The sum, I guess I should say, the sum of the area of each rectangle. So this notation, if you move on to take an AP calculus class, you really need to understand how to go back and forth between this limit notation and this integral notation. In this class, we're really just introducing the idea of finding the exact value of a definite integral, so finding the exact area under the curve. So we're not going to go into this notation too much, but what I want you to understand is that we can find the exact area by looking at the integral and evaluating it, maybe instead of by finding actual rectangles, but maybe in a more analytical way. Maybe we can use the function and what we know about the function and what we know about indefinite integrals, and maybe we can use that information to actually calculate the area under the curve without having to do all of this geometry rectangle business. That's what we're going to explore in the next video, which is on 4, 2, and 3, approximating the area using Riemann sums, definite integrals, part 2. So part 2 is going to heavily focus on how do we actually do this math without having to draw all of these rectangles. So to recap what we covered in this video, we talked more about using the notation for a definite integral, so having those numbers on the integral symbol, and how to practice drawing the rectangles for midpoint, right-handed, and left-handed Riemann sums and approximating the area. And then we wrapped up by saying that we actually can get a better approximation the more rectangles we have. And if we had an infinite number of rectangles, we could find the exact area, which is what we're going to focus on in the next video. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.